Very sorry for the inconvenience. Okay. So good morning all. So firstly, I would like to thank Dr. Narendra Rajgopal for providing this opportunity. Today we'll be discussing about the SIot and IIot specific routing protocols and models. So these are the topics that I'll be discussing. I'll start with introduction, then we'll move on to the evolution of IoT, IIoT and SIoT. We'll try to introduce a few protocols and the type of protocols, the models, and the demo. I'll try to give one demo where we have developed our own simulator specifically for social Internet of Things, and finally I'll conclude the session. So to begin with, in fact, everyone know that the definition or what is exactly an Internet of Things. Basically, it provides an interconnection of various network-enabled devices that are enabled through Internet, which basically used to interact or cooperate among the devices. Like we have sensors, actuators, RFIDs, smartphones, right? But the important thing is to achieve a common objective, which are basically can be applied to various applications, to where automated applications like power distribution or security, health, and as well as some agriculture. Okay. Now, if you look into the IoT architecture, we can see that there are three basic layers where we can keep on add. As a researchers, we can propose a new layer into this. Okay, so here we have a perception layer, a network layer, and also an application layer. Right now, especially from when we start this as a developer, we start with an application base. We think about some application where exactly this model or in a protocol has to be applied. Okay. Under perception layer, you have a set of physical objects, and especially when it comes to SIoT, we use several devices. There could be a public devices, a private devices. Under that, there could be a static devices or a mobility devices. You know, like we can go with traffic application like street light, and we have temperature sensors, right? So these, either when we talk about temperature, this could be a body temperature or this could be an environmental temperature. Okay, so there are various sensors as well as actuators will be used, and basically how these devices communicate or connects at the physical layer, right? So when you look into the connectivity, basically we have specifically to an IoT, we have Zigbee, right? And we have 802.15.4, 802.11, 802.16 as WiMAX. We have Bluetooth and also GSM, right? So these connectivity protocols that will be used. And when it comes to network, you know, so there are different set of protocols that will be used here. And at the application layer, in fact, in between these things, you know, there are a set of applications, you know, which basically we use to analyze the data, and finally you have to take some action. That's what when we look into the IoT definition, it says that D, I, and K are very important. One is data, information, and the knowledge. And these data are generated through various sensors, and we try to store these data and pre-process this so that it can be converted into some useful information that could be either you can store it in a cloud or you can store that in a local manner. Okay, and finally, by analyzing these data, we try to take some action out of that. So it means we try to make some decision out of that, right? So then only it completes the whole IoT things, right? Now, as a researchers, we have a different options. We can work on these uh, data collection process, or it could be in information storage, how we try to aggregate these data, right? And also how we store this information, or how we can manage, or we can take some action out of that, right? Now, the advantage of these IoTs are basically it enables the infrastructures where we almost we make use of wireless architecture and try to build an infrastructure. It means it provides a means for connecting objects with another object of a machine, and it enables the sensing or the decision making and also the actions that are involved in a everyday object. And also it is capable of communicating effectively within an environment. So where the device, say for example, our mobile phone can track my user profile, and it can suggest me what exactly I need. So if you take in healthcare applications, which is available in a mobile or a diet plan, so automatically it can suggest me what to eat, or when to stand up, or when to start walking, So it basically provides a lot of services to the users, okay? And it is capable of participating or making decisions which is relevant to its own destiny. It means we try to use this particular point in a social Internet of Things, where we try to consider the social the profile of an user. Okay. If you look into the set of protocols that will be used in an IoT by considering various applications, for an industrial IoT, you can use. In fact, there are different types of protocols available. So one is LPWAN, or an cellular, Zigbee, Bluetooth, Wi-Fi, RFID, right? Most of the industrial based applications use LPWAN, which basically uses star topology. And we have a smart meter application also uses this, smart city application, or a smart building. Sometimes even the cellular as well as Zigbee will also be used in an industrial IoT. But in most of the smart home applications, we try to use Zigbee as well as Bluetooth and also Wi-Fi. Okay, where you have a device-to-device communication, which are connected, peerly connected, and also, vertically as well as horizontally, it will be connected. Okay. And another certain applications like wearables, or a connected cars, or a connected health, So these things will use Bluetooth, some Wi-Fi also, right? So the smart retail, if you look into the card reader, basically it uses the cellular things, and Bluetooth as well as Wi-Fi. It means if you look into this, most of the applications basically depends on these the set of protocols, or the connectivity protocols that will be used. And when we talk about these connectivity protocol, how do we choose these protocols? Obviously, choosing the protocol depends on the application that we are using. And also, now once we say that, we have to develop some application. For that application, what will be the range of connectivity we require? So depending on the range of connectivity, right? And also the data rate, right? So this particular plot figure shows that what is the range of each protocols and the data corresponding data rate. Okay. Now, if my application demands a max of 10 meters, you can go with RFID. Or if my application demands 100 meters or a 10 meter or a 1 kilometer or an 10 kilometer, depending on these things, we try to choose the protocols. Okay. Now, once we choose the protocols, so how the data has to be transferred? Okay, what is the speed of the data? So up to 100 Mbps, we can transfer these data by using these set of protocols. Of course, nowadays most of the applications uses Wi-Fi as well as cellulars. Now, when it comes to device-to-device communication, so for example, if my smartphone wants to communicate with smartwatch, obviously we go with the Bluetooth enabled devices. Okay, right. And also the power consumption is also very important, where most of the researchers are working on energy aware routing protocols. Okay. Now this has led to a utilization of IoT in an industry. So industrial IoT basically happens in the manufacturing industry, which refers to the industrial, so where basically we call it as a subset of IoT, okay, where we try to collect the non-production data and we try to improve the industrial operations, and also we try to collect the product related data and improve the product life cycle performances. It means, especially in an industry, industrial IoT, one is with respect to operations and another is to analyze the data. So it means the devices are operating by connecting between its peer devices, and also where we try to analyze these data, okay, and we try to come up with a new decision model, okay, by using an IoT. Now, with respect to this context, whereas a different set of contexts will be used, like sensors and actuators. So these are the stages that are involved in industrial IoT. So basically, in stage one, you have a set of sensors as well as actuators, okay, which will be then utilized by a gateway, I mean the internet gateway, where the data acquisition system will collect all this data. So when it starts collecting the data aggregation, right? Okay, then that will be sent to an edge IT, right? Where we try to pre-process these collected data, right? And that will be sent to a data center, which is a cloud, where we try to analyze this data and manage these data, right? So in an edge stage, where it basically, so the development of sensing and actuation device that attaches to represent properties of industrial equipment or the product and also the materials. So for this, a gateway connect edge devices like the sensors and the actuators to the local network within the industrial organization, and the data management system, which provides a provision for a servers or a cloud-based system, right, which are required to manage and use this data associated within the edge devices. Okay. Now, we started with IoT and as a subset of this, the industrial IoT. And the emerging trend is the social IoT, where basically now world is moving preceding generation alpha, where which believes that socializing the object or a device within the network, and that is known as a social Internet of Things. Basically, this SIoT has gained a significant role in this current situations, which accesses the data and utilizes the intelligent system through a cloud platform. Okay. And these objects, we call these objects as a smart objects. It means these objects are capable of thinking. It means for the objects, we try to add intelligence to this. Instead of sending the data to the cloud, where the cloud will make some decision, rather than that, we try to adapt or build a knowledge model to the device itself, so that the device itself can take a decision. Okay, so the object models, which are very, very necessary for an efficient discovery of the services based on the context or the semantic relationship between the user and the objects. It means, strictly speaking, there are around 10 different types of social relationships, and these relationships are formed based on certain constraints. Okay, so if you look into the different types, okay, one is parent-object relationship, co-work object relationship, co-location, owner object, social object, guardian object, guest object, sibling object, stranger object, and service object. Now, how these relationships are formed? Now, how do we establish the relationship? So, in fact, the basic types can be defined as, one is user to object and object to object relationships. And these relationships are being categorized based on that. Okay, where you have a set of physical devices. Now, how do I use these physical devices? As a user, initially I start profiling this, which we call it as an object profiling. It means the type, the device type, the model, the manufacturing ID, right? So all this data will be fed into the object, so that by utilizing this, or these parameters will help us to establish the relationship. The constraints that will be used here are the device type, whether two devices that are communicating are of same device or of different device. So suppose if mobile and mobile are communicating, or whether mobile and watch are communicating, or is it mobile and camera is communicating? Okay, so that, and second thing is, the second parameter is the distance. What is the distance between these devices? So whether they are in the closed distance or which are away from the range, and also the type of connections that it is using, and what type of protocol it is using, and depends on the brand also. If both the mobiles are same brand, or if it is different brand. Now, depending on this, see, for example, suppose you have strange object relationship. If two devices are of different and the distance meter is less than 15 and they are using Zigbee protocols, if the brand is different, then we define it as a strange object. And also one more important parameter is the number of meetings also. Okay, so if two devices are frequently meeting, okay, then we won't call it as a strange object relationship. And each object relationships are established through these parameters. Okay, and this is not the only set of parameters that are used to say that or to categorize these relationships. Any researchers who is working on the defining the relationship, they can come up with their own relationship as well as by suggesting few more parameters to this. Okay, right? And this is what we have come up with. Certain the existing was something around 5 relationships conditions were there, and we based on some experimentations, right, we came up with these criteria or the constraints. Now, if for an object relationship, right? So, or for a parent-object relationship, let's say that. If devices are of same and the distance is less than 400 meter and the connection is primary, okay, and the protocol is either it could be Wi-Fi, Bluetooth, right, or Wi-Fi direct, and the brand is of same, then we call the we categorize that particular device as a parent-object relationship. Okay? So basically, this table is showcasing the set of how do we obtain or how do we get the relationship, establish the relationship between the devices and the type of relationship. Now, with this background for an social IoT as well as an industrial IoT, the type of protocols that will be used to define a protocol, right? Any network protocol is an established set of rules that determines how data is transmitted between different devices within the same network. With routing protocol is a process of selecting suitable path for the data transfer from source to destination. It basically follows two important things. One is route discovery and another is route maintenance. Okay. So while finding or identifying the route, right, it possesses several difficulties. Okay. So that basically depends on the type of network that you are using, the channel characteristics, and also the performance metrics. Okay. And the knowledge of network structure and the routing protocol is very, very important, and it should be an appropriate for the requirement of any usage. So at the end, a performance analysis of different routing protocols will be made using either WLAN or a ZigBee based WSNs. Okay. When we talk about routing protocol, it is between the devices. That's the reasons we use this as the wireless sensor networks will be used in this, especially when it comes to the physical connection between the devices. It is quite challenging because there will be a multiple characteristics which differentiate them, right, from an infrastructure to an infrastructure-less networks, right. It's almost difficult to allocate a universal identifier scheme for a big quantity of sensor nodes. So wireless sensor modes are not proficient by using a classical IP-based protocols. And also the flow of detected data is compulsory from a number of resources to a specific base station. But this is not occurred in a typical communication network. And also, the created data traffic has a significant redundancy in most of the cases because many sensing nodes can generate some same data while sensing. So it is essential to exploit such redundancy by the routing protocols and utilize the available bandwidth, and also suggest some efficient or an energy efficient as possible. And also, if you in this WSN, wireless modes are firmly restricted in relations of transmission, like energy or a bandwidth or capacity and the storage or an onboard energy. So due to such dissimilarities, a number of new routing protocols has been projected in order to cope up with these routing challenges in a WSN. Okay. So there are different types of WSN routing protocols. One is it can be categorized as path establishment, network structure, protocol operations, and initiator communications. So of course the path establishment or the route discovery, especially in social Internet of Things, we call this as an service discovery as well as
ऑप्शंस दी हुई है ना क्विज में, इसको फैसिलिटेशन कर देना अभी के लिए और इसका स्क्रीनशॉट क्लिक करके रख लो। अगर फाइनल में ऐसा कुछ आता है तो फिर हम रखेंगे, इसका स्क्रीनशॉट क्लिक करके रख लो। ठीक है, ठीक है देन। और कोई डाउट है?
हेलो,
हाँ वो तो मुझे भी पता है, हाँ वो पता लग गया, हम मल्टीपल ऑप्शन।
मैडम मैम sir, sorry for the inconvenience, sir. Kindly continue, sir.
Yeah. So under SIOT, this path establishment, we basically use two important terms, terminologies called service discovery and service composition. Now, while establishing the path itself, or when you start planning a path, the initial requirement is the type of services that you are looking for. You have n number of devices located, and which device is providing what type of services, and that services depends on the application that you are using. Okay, so suppose let's say I want to configure or find the best hotel, or I want to book a table in a very good hotel. All right. Now under social IoT, now these my mobile will decide or will choose the best hotel. How? It starts communicating with its devices that are connected to it. Now generally in Internet of Things, straight away it looks for the set of hotels or the restaurants that are available in a specific location. Whereas in SIOT, since the service is a restaurant, okay, here it first looks out for the set of restaurants available through the set of devices that is connected. Instead of mobile starts logging into the internet and searching for this, it finds the devices which are in relationship with this. If let's say some car is moving around that particular restaurant, now that car sends a message to my mobile stating that this particular restaurant is very good and there is a free parking, and the traffic application says that less traffic is available. Right now, how do I choose the path? The source is my location and the destination is the restaurant, and in between I have a set of devices involved in this, where the car is a mobile device, traffic signals are the static devices, and these devices starts communicating. Right? So that's what the path planning. The path planning helps us to discover the services in social Internet of Things. Okay. For this, in general, within an WSN, several reactive protocols, otherwise the proactive protocols and the hybrid protocols will be used. Okay, and then that depends on the type of protocol that you will be choosing. And when it comes to the structure, network structure, basically you have a flat, hierarchical, and the location-based structure. And the protocol operations could be multipath, or a query-based, or a bio-inspired, or QoS-based, or coherent, or maybe non-coherent. And the initiator of this communication is the source and destination. Now, how do we adapt this sensor WSN routing protocols to SIoT or an industrial IoT? Now, for that, not only we require these two, the source and destination, we take one more input as a service. And that service will be provided by the initiator, the user. That depends on the user, the object profiling. Okay, so if I am using my mobile and mobile belongs to me, and so I have mobile understands me, and I have some define some set of rules for that, like by creating some object profiling. Now, depending on the services, it starts choosing. So the initiator of the communication is source, destination, and also the services in a social Internet of Things. Now, with respect to protocols, of course, further it can be categorized as data-centric, hierarchical, and a location-based protocols. Okay. Under data-centric protocols, so of course, flooding, right? Flooding and grasping sensor protocols for information, the spin can be used, or energy-aware routing protocols, okay, or an a CADE, right, or an acquire can be used. And also, if you look into the hierarchical, the standard protocol is Leech, right? Low energy adaptive clustering hierarchy protocols can be used, or the Pegasus, or you have a TEAN or an Aptean. So when it comes to location-based protocols, MECAN or SMECN, right? So these protocols can be used. Now, to adapt it for an SIot as well as IIot, these protocols can be used in our case. The RPL, CORPL, CARF, AODV, loading, and also AVDV version 2. Okay. Now, to cope up with the limitations of IoT system, a routing protocol should meet the specific requirements and employ different strategies. Such protocols need to match the traffic pattern of its deployment area and be resourceful in terms of power consumption. And also, it has to scale in terms of memory and performance while being able to cope with sparse location changes. So for an IoT routing protocol, it is required to recognize and avoid one-way links and be conservative on the transmitter energy usage. Okay, so especially finally it has to use the IPv6, which basically we have to choose a protocol that supports IPv6, and mobility are very, very important. That has to be considered as an essential qualities. So when it comes to proactive and reactive protocols, of course, in a proactive routing protocols, we try to have a global view of the whole network topology every time. It means where we try to maintain a table, okay, or initiate the process where we say that the willingness parameter is very, very important in proactive routing protocol. Suppose if I take an example of same application, the restaurant finding, even though we have a shortest path between the source and the destination, if the intermediate devices are not ready to transfer these data or exchange these information, you cannot choose that particular path. So now how do I find this? Now, especially when it comes to SIoT protocols, or an IIoT, the features and also the characteristics that are very important here. The strategy that you are following, and also the traffic type, the mechanisms that we will be using, the algorithms, the support of IPv6, okay, and also the main features, okay. Now, if you try to summarize these protocols, the available or the existing protocols, the RPL, P2P, the CORP, or an loading, and the strategy that uses most of them are you can say that it's a mixture of both reactive as well as a proactive protocols. Okay. Now here you have a different set of protocols, right? And all these protocols supports IPv6. Okay. Now And also it addresses certain challenges, especially the challenges related to a IoT. Okay, right? So let's try to look into each protocols, right? First one is the RPL, which is IPv6 routing protocol for low power and lossy network. Okay. So it's a distance vector routing protocols for an LLMs that makes use of IPv6. Each network devices running this protocols are connected in such a way that there is no cycle present. So while building or developing a structure of this, we have made sure that, I mean, this protocol makes sure that there is no cycle. So that's the reason it uses destination, okay, destination oriented, okay, directed, acyclic, okay, graph, right? So the destination oriented, directed, acyclic graph, DODAG, which is routed as a single destination, right? So this RPL specification calls this specific node called as a DODAG route. Okay, the graph is constructed by the use of objective functions, which basically defines how the routing metric is computed. Okay, now it tries to avoid routing loops by computing a node's positions relative to the other nodes with respect to DODAG route, and we call that particular position as a rank. And it increases if nodes move away from the route and decreases when the nodes move towards the direction, respectively. And the rank may be equal to a simple hop count distance, may be calculated as a function of routing metric, or it may be calculated with respect to the other constraints. Now, the other constraints that we can focus here in SIoT are, it need not be the hop count, rather the set of services that are provided by the each devices and the type of protocol that each devices are using, okay, and the relationship between the devices. So we to update or to adapt this protocol to SIoT. I mean, this RPL is meant for IoT, of course. Now to adapt this to an SIoT based architectures, okay, so we can consider three more metrics. One is the relationship between the devices. When we say that the relationship between the devices, obviously it follows certain constraints like distance, the brand, the device type, the model, okay, the meeting frequencies and all. Okay, and also we can use the type of services that each device is producing or providing, and also the protocols that are used by these devices. Okay, in this RPL, four types of control messages are used to exchange or to communicate. The first one we call it as a DODAG, which uses the information object and is the main source of a routing protocol, since it acts as a route. It may also store the informations like current rank, the current RPL instances, and also the IPv6 address of the route. And the second is the destination advertisement object, okay, so which basically enables the support of down traffic and is used to propagate destination information upwards along the DODAG. And the third is DODAG information solicitation, okay, and which makes it possible for the node to require the DIO messages, which is used to find the reachability between the neighbor nodes. And the fourth type of message is DAO-ACK acknowledgement, which is basically sent by a DAO recipient in response to a message. And this RPL specification basically defines all these 4 types of control messages within an ICMPv6 information message, which requires a type 155. Okay, and if you look into the structure of a message, right, which is where DIO is a main source of information, right, which is required to construct the topology. Okay. So this is the RPL instance ID, the version number, and the rank. And obviously, we know that the rank basically are used to whenever you have an incoming devices as well as the outgoing devices. You know, it's like whether you can clearly say that whether you have a static type of devices or which can remain over a period of time within the connections. Okay. And it's of 32 bits, you know. So the first 8 bits are reserved for RPL instance ID, and next 8 for the version number, and the remaining for a rank, which basically uses the flags as well as the reserved memory, right? Optional DOTAG is of 128 bits. Now this DIO first allows a node to discover the RPL instance by storing the corresponding one in the first data field. The second and the third field include the DOTAG version and the rank of a sender message. Okay, and the next byte includes the G flag, which basically defines whether the DOTAG is grounded or not. Okay, right. The grounded means that it can satisfy an application defined goal if it is set, right, or not set, and it is said to be a floating. This may happen when the DOTAG is disconnected from the rest of the network. Okay, right, and also supports only connectivity to its nodes. And also this mop field is of 3 bit, which is set by the DOTAG root and defines the used mode of operations for downward routing. And the PRF field, which is 3 bits, define how preferable the root node is compared to other root nodes, such as a node is identified by the DOTAG ID fields. Okay, the last field DTSN and is needed for saving the sequence number. Such a number is maintained by the node issues the DIO message and guarantees the freshness of the messages. Okay, then how to construct the topologies? It basically 3 types of nodes in this RPL network. The first types are root nodes, which are commonly referred in literature as a gateway nodes that provides connectivity to other nodes. Second types are the routers. Such nodes may advertise topology information to their neighbors. And the third type are the leaves that do not send any DIO messages and have only the ability to join an existing nodes. So it means the initiators can be first 2. All right. Okay. The construction of this topology starts as a root node that begins to send the DIO message. Each node that receives this message runs an algorithm to choose an appropriate parent. The choice is based on the used metrics and constraint defined by the OR. Afterwards, each of them computes its own rank, and in case of a node is a router, it updates a rank in the DIO message and sends it to all the neighboring peers. Okay, so those nodes that repeat the same steps and process terminates when DIO message is it's a leaf or when no more nodes are left in the range. So, for example, to calculate the possible rank, right? The floor way evaluates to the greatest integer less than that or equal to v right? Floor of rank of minimum hop increase. Okay. So, however, in most of the sensor nodes deployment, several data collection points are needed. So, thus, three values have to be considered in order to uniquely identify a DODAG. One is the RPL instance ID for identification of an independent set of DODAGs, like optimized for a given scenario. The DODAG ID, which is routable IPv6 address belonging to the root, and the DODAG version number, which is incremented each time a DODAG reconstruction is needed. The RPL specification defines the combination of those three values as a DODAG versions. Okay, so this is an example of the construction of topology where the different versioning number will be provided, like DODAG ID1, ID2, and ID3, depending on the number of nodes that starts choosing its clusters. You know, okay. And further, which has been used or to improve the performances, P2P RPL is standardized. It's a reactive RPL that basically enables an IPv6 router in LLN to discover the paths to one or more IPv6 routers in an LLN on demand. Enhanced RPL is an enhanced enhancement for an RPL protocol aiming at enhancing its reliability. DRPL, which is a dynamic RPL for the dynamic applications of an IoT, which improves the energy efficiency of a network and end-to-end delay, and more importantly, it adapts to the mobility changes better than the RPL based protocols. And also we have MRPL is the mobile versions of an RPL, which basically focusing on the mobility management in an IoT environment. And the second one is the CORPL, CORPL, which is a non-standard extension of an RPL that is built for a cognitive network and employs DODAG topology generation. So it uses an opportunistic data transmissions to forward the package by choosing multiple forwarders. It coordinates them so as to choose the optimal next hop to relay the package to the DODAG and is designed similarly to an RPL. So every node keeps a forwarding set instead of its parent only, and informs its neighbors with its changes using DAG information object messages. So according to the update information, every node dynamically updates its neighbor priorities so as to build the forwarders. It's a channel-aware routing protocol, which is basically used in an underwater sensor networks. The car, its asset includes delivering packets in reasonable time with low energy demands. But in addition, it enables it is able to support link quality information that is calculated from horizontal, historical successful data transfers. The history is collected from an adjacent sensors in order to choose these forwarding nodes. The main weakness of this CARP is that it does not allow reusing previously generated data. Okay, and the enhanced version of this is the eCARP. Okay, right. So it allows the sync node to save previously received sensor data. Hence, we use this eCARP drastically decreases the communication overhead. Okay, and further the AODV loading and AODV version, basically these are classified based on the hop by hop reactive protocols. Okay, so where we use root request as well as root reply cycle that is initiated each time a packet needs to be transferred an unknown destination. Okay, right. Now Strictly speaking, in an AODV, ad hoc on-demand distance vector of this loading, okay, where you have a lightweight on-demand distance vector routing protocol, the next generation NG, and also the AODV version 2 are the successors of AODV basically, So which just uses the hop count as a routing metric. Okay. So when we say that this hop count as a routing metric, most of the SIoT based applications or the social Internet of Things applications can use this AODB whenever you are trying to locate or you are trying to find the services which are not available within the relations. Whereas now, how do I find this? How to find these services or the set of devices that are available within a distributed environment? Okay, so for that we can use certain machine learning models to identify. Okay, and when you look into the AODV, there's versions. Okay, which is basically suited for an resource limited network environment like AODV base, VGR, coding, low pan AOD, NST AOD, or a tiny AOD. Okay, so all these things can be utilized in an SIoT based applications like smart city or in the prediction of restaurants, available restaurants. Okay, right. And another protocol is the CTP, which is a tree-based collection protocol, where some number of nodes in the network advertise themselves as a tree roots. The nodes form a set of routing trees to these routes, and CTP is address free in that where a node does not send a packet to a particular route. Instead, it implicitly chooses a route by choosing a next hop. Okay, the nodes generate the routes to other routes by using a routing gradient. Okay, there are certain assumptions made in CTP protocols which assumes that the data link layer provides 4 important things. One is the efficient local broadcast address, a synchronous acknowledgement for an unicast packets, a protocol dispatch field to support multiple high-level protocols, and it has a single hop source and destination fields. Okay, so it provides an estimate of a number of transmission that it takes for the node to send a unicast packet whose acknowledgement is successfully received. And this CTP has several mechanisms in order to improve the delivery reliability, but it does not improve or it does not promises 100% reliable delivery. And it is designed for relatively low traffic rates, and the bandwidth limit system might benefit from a different protocol, which can, for example, pack multiple small frames into a single data link packets. Okay. Now, with respect to the collection and the CTP of this CTP protocol, it uses ETX, expected transmissions, as its routing gradient, a route as an ETX of 0. The ETX of a node is the ETX of its parent and also the ETX of its links to its parents. This adaptive measures assume that nodes are link level retransmissions. Given a choice of valid routes, the CTP should choose the one with the lowest ETX values. And also the CTP represents the ETX values as a 16-bit fixed point real numbers within a precision of hundreds. An ETX value of 451, for example, it basically represents an ETX of 4.51, while ETX value of 109 represents a ETX value of 1.09. Okay, it assumes that the problems that is faced by the CTP are the loops, the routing loops is an that can emerge in a CTP network. And the routing loop generally occurs when a node chooses a new route that has a significantly higher expected transmissions than its old one. Perhaps in response to losing connectivity with the candidate parent. If the new route includes a node which was descended, then a loop occurs. Okay. The packet duplication is also another problem where which can occur when a node receives a data frame successfully and transmits an acknowledgement, but the acknowledgement is not received. So the sender retransmits the package and the receiver receives it the second time. This can have a disastrous effect over the multiple hops as the duplication is exponential. For example, if each hop on average produces one duplicate, then on the first hop there will be 2 packets. On the second there will be a 4, and the third will be 8. It goes on, you know. So the CTP faces packet duplications, and also now to address this, okay, the enhanced CTP contains certain nodes gradient value. If CTP receives a data frame with a gradient value lower than its own, then this indicates that there is an inconsistency in the tree. And CTP tries to resolve this inconsistency by broadcasting a beacon frame with the hope that the node which sent the data frame will hear it and adjust its routes accordingly. If a collection of nodes is separated from the rest of the network, then they will form a loop whose ETX increases forever. The second mechanism is not to consider a route with an ETX higher than a reasonable constraint, and the value of this constant is implementation dependent. Okay, so the data frame looks like this, where the PC, the reserve, the THL, the ETX. Okay, right. So these fields, the P basically use a routing pool, which will allow the nodes to request routing information from other nodes. If a node with a valid route hears a packet with the P bit set, it should transmit a route frame in the near future. Otherwise, no. C bit, which is used as a congestion notification. If a node drops a CTP data frame, it must set the C field on the next data frame it transmits. The THL, which is a time has lived, right? So field, when a node generates a CTP data frame, it must basically set the THL to 0. When a node receives CTP data, it must increment the THL. If a node receives a THL of 255, it increments it to 0. And the ETX, the routing metric of a single hop sender, when a node transmits a CTP data frame, it must put the ETX value of its route through the single hop destination in the ETX field. If a node receives a packet with a lower gradient than its own, then it must reschedule or schedule a routing frame in the near future. The origin field, which is the originating address of the packet, a node forwarding data frame must not modify this particular field. A sequence number field, or which the originating node sets this field, and node forwarding a data frame must not modify this. The collect ID field, which is a higher level protocol identifier, again the origin sets this field, and a node forwarding a data frame must not modify it again. And the actual data, the data payload of 0 or more bytes, a node forwarding data frame must not modify these data. Okay, so together the origin, the sequence number, and the collect ID fields denote a unique origin packets, right? So, and the THL denote a unique packet instance within the network. The distinction is very important for a duplicate separation in this presence of routing loops. If a node suppresses the original packet, then if asked to forward the same packet twice due to the routing loop, it will drop the packets, which by providing a solution to the duplication of these data. However, if the suppresses packet instance, then it will route successfully in the presence of a transmit loop, unless the THL happens to wrap around to a forwarded packet instance. Okay. Now, for these to adapt these routing protocols, I mean IoT-based routing protocols to an SIot and an IIot, there are certain models that can be adapted to this. Okay, especially the two dynamic routing models we have are the hub model and a distributed model. Okay, so the hub model is a traditionally that has been used by a dynamic transaction routing, whereas in the distributed model, each region may be both a routing region and a target region. Okay, the hub model looks like this, where basically the transaction starts from the terminals, and these started by the terminal start with a start command. The program link requests this received from the outside. Okay, in an hub model, multiple the possible target regions that are trying to connect to this device, I mean the dynamic routing region. Okay, they start initiating through the commands, and the program link will be created between this. Okay. The advantage is it is very simple, relatively very simple model to implement with respect to the distributed model, where you have an inter-region connection. Okay, the disadvantage is if you use only one hub to route transactions and the program link request, and it is a single point of failure. So it means when you have a distributed data, if the route if you fail here, or if the single point of contact fails, the whole network fails. Okay, so the onion router network is a secure encrypted protocol that can ensure privacy for data and communications on the air. It uses a series of layered nodes to hide IP address, online data, and browsing history. And the distributed model, where the transaction service processes and activities are distributed over a region. The distributed model is a peer-to-peer system, and it is non-terminal related to start request. Okay, so where each devices are, each peers are distributed within a system based on the regions. Okay. So here you don't have the advantage is there is no single point of failure, where the disadvantage is if you try to compare this with a hub model, so there are many inter-region connections which is very difficult to maintain. So especially in an IoT based applications, when you have a distributed model, so there could be it's a best solution, but very difficult to manage this when we adopt this model. Okay. Basically, if you take an example of a smart city applications, which is a distributed environment, where several devices are distributed over an region, which can involve both public devices as well as the private devices. Okay. And each devices have a relationship between another devices. Okay. Now, each device can have various protocols enabled inside that. It can have a Zigbee, it can have a Wi-Fi or a Bluetooth, any type of protocols. In this particular figure, you can notice that you have both public devices as well as the private devices, and the connectivity, the network, which all the devices are connected, and you have different types of protocols, and each devices have a relationship between each other. Okay, so the devices are randomly distributed here. Okay, so we can use this particular model, the distributed model, for an SIoT based applications. Okay. Now, to understand this in a better way, right? So, especially for an SIoT based applications, I have a small demo of a simulator. Okay. I'll just go through that. I'll just start presenting that. Okay. Then we'll come back to the slides again. Can you see this? Okay.
Yes, sir, it is visible.
Yeah. So
Yes, sir.
basically, yeah. So this is an interface that has been built for an social Internet of Things, where we try to consider three different scenarios. One is the existing, which is nothing but where we have to create or establish the link between the devices. Another is we try to drag and drop those devices and automatically it generates the link between the devices. And third one is providing an environment. Okay. So let me go to the dynamic environment first. Okay. Right. So in fact, this is the simulation area, you know, where can you see the simulator? Hello.
Sir, your screen is not visible, sir. Oh. Now it is visible, sir. Visible.
Oh, I think I missed the first interface, I guess. Okay. Anyway, this is the simulation area. Okay. So here we have different types of devices, you know, like public devices as well as private devices. And also, this is a very important field where the object profiling. So these objects are identified through device ID, device, the device type, the device mobility, okay, the owner ID, the manufacturer ID, the service ID, application ID, and the type of connectivity. Okay. Now, let me try to add few devices. I'll try to add some 5 smartphones. Okay. One static printer. Let's say another some 2 tablets. Okay, and few street light. Okay, one more, right? Some 2 car, which is a private device. Okay, and something or some 2 to 3 smartwatches. Okay, right? Now, basically, what we are trying here is, initially we try to build a relationship between the devices. And when we talk about devices within a social IoT, right? So profiling, right? if you look into this, where we have created in such a way that each device profile has been made sure that if you click on the device, you'll get the details of it, right? So that the device ID, the smartphone, right? In this example, I tried to select mobile, so smartphone, it's a private, okay? Then okay, so again, device type is mobility, and the device is car in this case. And if you click on this, this is another device, okay? And if you click on the street light, okay, you can notice that this is a static device, right? So where basically we try to categorize any devices in an SIoT based environment as a public device as well as the private device. Under that you have a static as well as a mobile devices, right? So and we have a certain few more applications. I can add one more point of interest or some transportation or some alarms, okay, or some home door sensors, right? Now the basic idea or the utility of an SIoT based application is finding the relationship between these devices, okay? And of course I can this particular simulator can be used where I can disable the ranges also and enable the range, and these ranges basically defines what type of protocol it is using. So this is a smartphone which uses a Wi-Fi as well as a Bluetooth, okay? So this, okay, right, each device shows the type of range it is using, okay, right? So let me start this simulation, right? Let me run this for 10 seconds, okay? Before going to that, suppose, I have to enable or fix the parameters for these devices, like the relationship parameter. Now, suppose we have already defined. So I showed you in the presentation the set of parameters that have been used to define the relationship for STOR, for SOR, for GSTOR, SROR, CLOR, right? And for example, suppose this is STOR. Now we have made sure that it is different and less than 120 meters. And the category device type is private, okay? It's a public device, right? And it uses ZigBee. And the manufacturer can be different, and the intersection is 0. As a researcher, okay, you can edit these things. Suppose you feel that I don't want this distance to be 120. Or you can modify this. You can make it as 130, right? Or 110, and you can update these conditions also. Okay, right? And this particular simulator will provide all flexibility to make certain changes and conduct experiments. Okay, so before starting the simulation, okay, so very first thing we are supposed to do is check the conditions or set the conditions depending on the type of relationship, and this interface will allow us to modify the parameters. Okay, now suppose for stranger object I don't want the ZigBee, I can use a Bluetooth also, no problem. You can do a multiple selections here. Okay, now I have updated this, right? So this is the simulation environment, and these are the set of devices, right? And the object profiling has been done here. Okay, now you can notice that when I click on any object, the profiling changes, right? Okay, and these profiling, what we have done is we have randomly generated the value by considering certain specifications. Now, if you look into this, the service IDs are, we have something around 16 services, okay, for 26 applications. We have considered something around 26 applications and 16 services for this, okay. So randomly we are assigning a set of services just to conduct an experiment. Now further, any researchers can modify this and they can start conducting an experiment. Now for a social IoT, the important thing is the relationship between the devices. If you remember, at the start of the simulator, there was 3 interfaces: existing, dynamic, and environment. Okay, whereas I selected the dynamic environment, where I don't have to explicitly establish the relationship or connect between the device and identify the relationship. Rather, instead of that, in a dynamic mode, automatically we'll get this relationship. Now, it's basically, it's not a magic, right? How do we establish that relationship? Let me start this simulation. Please observe this. The mobile devices are moving. The statics are constant. The static devices are constant, right? Now, what basically we tried here is, we tried to change the distance. We made sure that in a realistic environment, the mobile devices changes its positions, right? The street length remains constant, right? We tried to simulate this. Now, when I say find relationship, okay, please observe this, okay, right? The relationship between these 2 devices, okay, is SOR. Whereas if you observe this, between this device and this smartwatch, you have GSTOR, right? Okay, fine. Now these are established based on the conditions that we have imposed in this. Okay, so further, suppose I want to extend this, or I want to conduct more. Yes, definitely you can do this. Okay, now you can see this. You have, see this particular device and this has a relationship of CLOR. Right? Now, the conditions for establishing these relationships are basically depends on this. Since we have selected these different criteria and we have defined this set of added these constraints to the devices, depending on this, right, this relationship has been established. Okay, right? Now, if you look into the results section, right? So I don't want to present these things. Rather, let's go to the navigation part of this, where our this particular topic focus is on routing. So under this, right? So if you choose any destination, let's say D1 is a source and D10 is a destination, right? Now these are the metrics that we have used. Can you see this? This is a results section. Okay. Basically our focus is on the navigation. So right now I choose the D1 as a source and D10 as a destination. Okay. We have a different options for this to find the paths. Right. Okay. Either based on the relationship between the devices or based on the protocols that we have defined, like whether you want a set of devices that are using only Wi-Fi, or I can choose both Wi-Fi as well as GSM, right? Or all, okay? And also, suppose I want to find a device or a set of device which are providing similar kind or the same set of services. And this simulator will also help us to do this. Okay, so let me try to, and also here we have a dynamic model as well as a theoretical methods, where in fact this simulator is an AI-enabled simulator. We have used machine learning models which has been already trained to cluster as well as classify these devices. Okay. Anyway, I won't go to the machine learning part. Rather, let's try to show the path, right? A set of devices, okay, between these D1 and D10, which are GSM and Wi-Fi enabled. And also now I can choose all these options and say show different paths. Okay, we don't have all the devices, right? Let's say I'll enable these two. Okay, and right, if I use some routing algorithm, okay, it's calculating and right. And that basically depends on the number of devices that we have used. So let me. So this is the path between the source and the destinations. Okay, these are the shortest path between this. Okay, and where we can show the paths and also. Just a minute. Yeah. Okay. Further, the results can be used based on the services, right? And we can plot this, or I mean, you can save these results. Okay. So you can change this source and okay. Now we'll go back to this and let's say Okay. Now let me navigate to environment model. Okay. So basically, this is an environment model, or see where in the previous case we tried to choose individual devices and try to establish the relationship between those devices. Now here, since most of the researchers, what we'll do is we don't want just to create a device or to identify, find a device and establish a relation. Rather, we try to create an environment, right? So we have provided certain built-in environments, right? It means there are set of applications where we can straight away load those applications. So for example, traffic application, okay? And also let's say parking application. Now the advantage of our city consumption, some application, okay? And also let's say any fire detection application, right? Now the advantage here is we are not explicitly identifying or finding the devices and adding to this. Rather, we have already created a set of environment applications which has the services inside that. Okay, each application has a set of services like locations, date, time, a point of interest event, people presence, environment, weather, energy consumptions, right? There are set of services that are available, and these services are already embedded within the applications. Okay, so where I don't have to create one more application, or if any researchers who wants to work on this, they can straight away load these applications, and indirectly they are loading the services inside those applications. Let's say that this is an application, okay, right? Now this application has only one service, right? Okay, so let me try to add few more devices to this. Okay, 2 mobiles, alarms, or some tablets, or some watches, right? Or some car, right? Okay, now where to load these applications? We have an option for that. I have choose a device. This device can be used for any of these applications, right? Okay, so device can be used to any A10 application, or there's any another device. You can choose device 4 and add it to A8. Okay, so you can add more devices into this, right? So where all the anyone who wants to work on these things has a flexibility to add this. So let's try to simulate this. Okay. See. Okay. See, basically, in a static environment, I mean the existing environment, where individually we are supposed to choose these applications or the devices and establish a relationship. Here this simulator helps us to find the relationship between the device based on the constraints that has been imposed on these devices. Okay, so of course you can see the results. Okay. We'll look into the navigations and say that any destinations, right? You can choose any specific services, whatever the services that has been added there. Okay, so that will be shown here. Okay, right. Okay, which basically gives the path between these devices, and it uses relationship protocols as well as a criteria to this thing. So what we can do, or as a researcher, what we can do? So we can add few more algorithms into this. In this case, we have considered only SIot and algorithm. Okay, we can add any type of protocols. In fact, yes, of course, there are Cisco protocol. I mean, the simulator is available for this. Okay, the packet tracer, which basically helps us to find or simulate this environment. You have an specifically IoT simulator, UJA simulator, which uses a Quantic operating system, right? This particular simulator, whatever we have developed, specifically meant for social Internet of Things, because in those existing or the available simulators, we don't have an option of, or we don't have an flexibility to add the relationship, since SIot defined based on the relationship between the devices. Okay, I guess in the morning session you might have heard about like what is the basic working principle of an SIot. You know? So there you could have noticed that we try to understand the social behavioral of a user, and depending on the user profiling, the devices are enabled in such a way that the devices understand the user's activities, and based on that it configures. That's the reason SIot has the composition component, or owner's control, or trust management. Okay, so there are different trust areas which can be focused as a researcher to propose certain models or to work on those things. And when it comes to specific routing protocols or the models, you know, there exist some as discussed, few protocols that are available which are specifically meant for IoT. Now, along with that, we can come up with our own protocols. In those cases, the metrics could be number of hops, right? So where we try to find the shortest path between those. Yes, of course, you can retain the same number of hops as a criteria here, or as a metric. But along with that, how do we choose the path? Of course, very important thing is the relationship between the devices. When I say whether it is using same set of protocols, we don't know, right? And especially right now we have simulated only few set of devices. When it comes to a real environment, you know, there will be a n number of applications, n number of devices, and n number of services that will be provided. Now, suppose I want to list out or find a specific device which is providing me a set of services and the required services. Of course, we can go with a machine learning model into this, where we can cluster these devices based on the protocols that it is using, or based on the relationship we can cluster, or that based on a specific services that these devices are providing, and also a set of private devices, public devices, okay, or set of static devices or a mobility devices, right? So depending on these things, we try to classify this and then apply these routing protocols for those devices. Okay. In fact, this simulator, right? So I'll just that's the reason we have provided 3 interfaces for this. Just this, yeah. If you observe this particular simulator, right? We have 3 modes. One is existing, dynamic, and environment. Because in the existing, we won't find the relationship, rather we establish the relationship manually. We are supposed to establish that. Okay, right? And I can just show you that the manual say this. This environment will help us to enable this. So where I have to provide these devices with a set of parameters. I have to specify what is the object ID, what is the owner ID, and owner the name, the manufacturer ID. Let's say this something, service ID 4, application ID 3, or some 6. Okay, right? And we have to choose this private or public or this, and where we can. Okay, where we can fix the size here. I mean the range, right? The initial battery capacity for each thing. Okay, right? And once we add the devices, okay, the existing, so once we start adding those devices, right? So we have to establish those relationships, whether it is SO or GO or right. So instead of that, these dynamic, okay, let me show this. This particular environment, whatever we have, this basically gives us the flexibility to choose among these, whether I want to use the dynamic or the environment. For a researcher, it is always better to use the dynamic as well as environment, because once I drag and drop multiple devices to the simulation area, where I don't have to manually establish the relationship, choosing the devices. Instead of that, I can straight away, depending on the navigation or the constraints, right? I can straight away choose those applications. I mean, choose the devices, right? Configure those parameters, and then I can straight away simulate this and find the result. Okay, so this is a simple simulator which is specifically designed and developed for an social Internet of Things. Okay, right, right. So okay. So to conclude this, basically SIOT is an emerging paradigm of an IoT, which is different from IoT devices interact, and the way it establishes connection with each other to achieve a common goal. So there are several OSs that are available for IoT devices, where we can choose a specific OS and an hardware building for a particular IoT application in a critical task. And same thing can be you can develop and industrial based applications and simulate within the same environment by considering social aspects of these devices. So in fact, at present, a few of my research scholars are working on construction equipment technology, where we are trying to establish the relationship among the devices and find the shortest path also. And one of my another candidate is working on developing a knowledge model for an SIot based the object-to-object interaction in SIot, and another is working on an ambient assisted living, where we try to come up with an reasoning model, the decision-making model, and so on, So definitely we have a lot of scope under social Internet of Things as well as industrial IoT. Especially when we bring on certain social aspects into these devices and provide some intelligence to these devices, where these devices can make their own decisions. Okay. Thank you. Let me open for questions.
Dear participants, if you have any queries, you can unmute your mic and ask, sir. Any queries?
Excuse me, sir.
Yeah.
I have joined little bit late. Which simulator you have used to demonstrate all these things, sir?
Yeah, madam, we have come up with our own simulator. Actually, we have in our lab, we have developed our own simulator called AI-based simulator for SIot. So where we have adopted certain machine learning algorithms to classify and cluster these devices depending on the parameters, and we are enhancing this simulator with more protocols into this in the due area near future, actually.
Okay, so is it accessible, accessible for us also?
No, madam. Right now we have not yet released. We are just waiting for an publication. Maybe in another month or so, we'll be opening this, and we'll be releasing the simulator.
Okay, ठीक है sir. Thank you.
Thank you.
Sir, there is a question in chat box. They're asking, can you suggest any other simulation tool?
Yeah,
for
yeah,
SIot?
Yeah, I mean specifically for an SIot, you have a demo, demo assist actually, ASSIST. There is a simulator. But that simulator is for an where manually you are supposed to establish a relationship between the devices. In fact, that basically made us to come up with or develop this simulator. Okay. Assist is a simulator which you can use. It's a proprietary. And also, if you visit socialiot.org, there is a link for generating the data to. They have provided a channel where you can connect these. Whatever the data that you, the environment that you have set up, and you can connect it and you can generate those data. But even they don't provide a simulator basically.
Participants, any queries? Sir, can we conclude the session, sir?
If no queries, yeah, madam. Okay.
Okay, sir. True and lasting success is all about taking it to the next level. But in order to get there, we first have to stand on a strong foundation. Without any doubt, I can state Sir had laid down a strong foundation to these 5 days FDP. Your demo gave an insight and confidence to do further research in this area, sir. I'm sure that the researchers will take your suggestions to move forward. On behalf of the Department of CSE, NIT Puducherry, I thank Dr. S.P. Sivaprakash sir for his flawless presentation towards routing protocols and models. Thank you for your valuable time, sir. Thank you.
Thank you. Thank you.
Thank you, sir.
Thank you all.
Participants, thank you all for your active participation.